Okay, I'm going to talk about the geometry and the quantum Hall effect, which is a kind of topic that at least a subset of people have been interested in quite actively recently. And I'm going to talk about some kind of hidden aspects of the Laughlin state that have taken a long time to emerge. And I'm going to call this quantum geometry. Okay, so let me just start. So the quantum Hall effect, in its simplest form, is a relation between electric charge density and magnetic flux density. And of course, if I have a relation that the charge density is proportional to magnetic flux, it also has to satisfy a continuity relation for charge. And this is, of course, underlies the reason that the Hall constant has to be a topological invariant, because this is only consistent with the Faraday law if I can kind of pull the sigma h constant inside and outside the derivatives in this thing. So the basic property then that's a consistent property with a conservation law is the electric current being proportional to the J mu being proportional to the curl of the vector potential. And so it satisfies continuity. And okay, maybe I'll go into this later, but I'm going to interpret in an effective theory of the quantum Hall effect. The basic entities are going to be somewhat analogous to a unit cell in a solid. It's a unit droplet in the quantum Hall state. And if you look at this thing a bit more closely, instead of just thinking of a filling factor P electrons with Q fluxes, in a sense, the things the effective theory knows about is the charge on the basic object that condenses, the composite boson, the statistical spin of the composite boson. So you see these numbers P and Q in this rational number are not, they don't have to be the lowest common denominator. In fact, they can have a common factor of 2, up to 2. So the elementary charge is just E over Q, which is really PE, the charge of the droplet, divided by the quantity which is the statistical spin of the composite boson. And the statistical spin of the composite object has to balance any kind of microscopic Pauli type statistics of the underlying particles this is made of. So if the charge E particles in this theory are fermions, then we get a quantity that, if P and Q had to be relatively prime, would be what was used to be called the odd denominator rule. But in fact, they're not necessarily relatively prime. And okay, so this is a kind of underlying phenomenology of the condensate, which I'll come to. But I'm going to be interested in the metric. And the basic point I'm making is that any non-singular positive definite tensor of rank 2 can define a spatial metric. So we don't immediately know a priori what the metric is. And in fact, all such metrics which are non-singularly related will have the same Gauss-Bonnet sum rule when they integrate them over a closed manifold. And then so there's lots of physical places where a metric can emerge from. And then any such metric, provided it evolves in a non-singular way by diffeomorphisms in time, etc., also has a locally conserved Gaussian curvature. So that makes the local conservation of Gaussian curvature makes a more general quantum Hall relation possible. Instead of just the charge density being proportional to the magnetic flux with some topological numbers, it can also get a term where it's proportional to the Gaussian curvature density times some topological numbers, which turn out to be spins which have to be integer or half-integer quantized to satisfy a condition of Gauss-Bonnet and a condition that the number of independent states of the basic droplet, the composite object that you can put on the surface if it's closed, has to be an integer. So I've written a sum over metrics here. And the key, because actually you can have more than one possible physical metric in the problem, and each such independent metric has its own spin associated with the curvature coupling to it. So the key question in interpreting the geometry locally, as opposed to global counting of states, which will be the same for all metrics because of Gauss-Bonnet, is which metrics are coupled in this way and how many other are and what their physical origin is. Okay. So if I actually think about this, we're actually doing something slightly different from standard metrics. It's not a space-time metric, but it's a spatial metric that's a function of time. So in fact, in this crystal, we have the background in which the electrons moving can be, they can be treated as moving non-relativistically relative to a crystal, which provides a preferred inertial background frame. So we basically have a kind of Newtonian space-time. The preferred inertial frame gives you some kind of Cartesian coordinate system out of its Euclidean metric on the 2D surface, and there's a time direction which doesn't have any relativistic coupling between space and time. And then we have these metrics which are internal properties or physical properties which are functions of space and time in this flat background. And if you go through this, there are a few little surprises, or there were for me in working all this stuff through. It's not exactly this. It differs from just Lévy-Civita for the space part, or because of the time dependence. So I have, in fact, if I look for a minimal metric compatible connection in space-time for this, we end up with these Christoffel-type symbols which have space-time indices in their lower left, but only spatial indices in the top and right. And when you work out the minimal metric, the minimal connection, which is the one which is expressible only in terms of the metric itself and its derivatives, and the same spirit as Lévy-Civita, you end up with that the time dependence only includes the first of the terms and doesn't include the kind of antisymmetric part here. And then you get the whole thing, you get some slight differences in the, interestingly, what this does for you, this is a connection which ends up having torsion, because of the torsion is related to the time dependence of the metric. So we have a connection, one form, a torsion two form, etc., and the curvature form. Again, as the differential forms, they only have indices which are space-like, spatial indices, and we have then this torsion thing. And I was actually working through this, I was wondering where in this formalism the conservation law of Gaussian curvature was hiding, and it turns out to be the second Bianchi identity, which gets modified by the presence of torsion. The first Bianchi identity actually gives you an expression for the spatial current of curvature. Okay, and then we're going to come back to this at some point. Then we actually, out of this thing, if we want to write something, various coordinate-independent structures, we'll end up with something very much like the geometric, the Chern-Simons form, the gravitational Chern-Simons form, except it's slightly different because we're tracing only over spatial indices. So I'm calling this the geometric Chern-Simons form. And of course, as this is the exterior derivative of this is the Pontryagin form with the spatial indices. This is, again, almost coordinate independent up to the boundary. Okay, so where's geometry actually going to come from? That's going to abstract about I've got some field inside here which is a metric which provides a meaningful physical definition of length scales. And the immediate obvious source of geometry is what is really a kind of background field, is just the effective mass tensor that you plug into this. So if I just take a particle in a magnetic field, in a coupled to electromagnetism, and give it, and instead of just having a delta AB, a Euclidean metric times a gravitational mass here, a more general, a metric, an effective mass tensor which has its origin in band structure, then one can work through this thing. The Hamiltonian just has the mass tensor, which is spatially dependent, sandwiched between the momentum operators, which really just reconstructs the Laplace-Beltrami operator, and the Lévy-Civita connection. Instead of putting GAB, I've put the mass tensor in here. And MAB with upper indices is the inverse of the mass tensor. Okay, so the basic point is that in effective mass tensors is not a Newtonian inertial tensor. So there's been a tendency in this field for people to kind of model the quantum Hall effect on Galilean invariant Newtonian physics. But actually, it's got nothing whatsoever to do with the Newtonian inertial mass tensor because it doesn't exist inside condensed matter. These are electrons which are moving around. They inherit their kinetic energy from a band structure coming from a microscopic scale periodic potential. Okay? And in fact, the mass tensor derives from a expansion near a band minimum, which actually will have higher order terms in here too. So it's not just a quadratic form as in a Galilean invariant Newtonian system. And secondly, the point I make here is that the electrons, they're typically in the Landau level structures, at least, they're typically bound to a epitaxially grown quantum well on a lattice plane, which is really flat, right? Lattice planes really don't like Gaussian curvature. They like to stay flat. It strains the bonds too much. So basically, the point I'm making here is you can have electrons bound to a geometrically perfectly flat lattice plane which experience a curvature not because of a physical embedding of this surface in Euclidean space and an induced metric, but from the variation of this chemically dependent or this chemistry and structure dependent field which emerges from the condensed matter background. And again, to the extent that the electrons are moving, that we're neglecting the phonon structures, the phonon degrees of freedom of the crystal and its strains, and for the moment just treating the crystal as perfect, then it's defining this inertial frame, and provided the electrons move non-relativistically with respect to that, the actual Euclidean spatial metric, which is used to set up a Cartesian coordinate system, has no role whatsoever to play in the physics. It only has a role to play when you have some gravitational effects, like you spin the crystal and get Coriolis forces and stuff like that. Then you'll pick up real, the spatial metric. But otherwise, everything is coming from this condensed matter system. So if I take this system, this is, of course, an identical set of equations you'd write down if I was imagining that the Riemann surface I was putting this stuff on was derived from, embedding in space, because Gaussian curvature is really kind of neutral to where it comes from. It doesn't need to know anything about the extrinsic, the situation that gave rise to it. Again, if you work through this, you find for this background thing, the Euler equation of the simple classical one-particle Lagrangian, just the acceleration gets replaced by the geodesic, the equation to get in the geodesic equation. So without a force, the particle would just move along the geodesics of the mass tensor. Okay, so this is actually an interesting problem that's been solved mathematically way back in the 80s. So if you have so you can ask, when does this system give you degenerate flat band Landau levels, right? So we're all kind of rather familiar with it on the sphere from the quantum Hall practices, but it works also on it doesn't depend on the Gaussian curvature being positive or negative. There's an equally good mathematical solution on the hyperbolic plane. And to get these flat band, these macroscopically degenerate Landau levels, the conditions are, first of all, just as on the flat surface, the constant effective mass tensor, that the cyclotron frequency has to be constant. But the other condition is just that the Gaussian curvature has to be constant too. So one gets this formula, which again was what we wrote up at the beginning, and is what goes back to Wen and Z and interpreting Wen and Z and things, is that you have if I look at the charge density of a filled Landau level, it just has the part proportional to B, and then a part proportional to the Gaussian curvature density, which is the Gaussian curvature times the root of the metric from which it's derived, and the determinant of the metric. And then there's this spin, which is a half in the lowest Landau level, 3 halves, etc. What's quite interesting, which I didn't know until I don't know if it's how well known it is, it's until I dug up this paper of Comte's, is that when you have the negative curvature, there's the Landau levels stop after a finite size and a finite number, and then you have a continuous spectrum. So when the energy gets too high, the orbits fail to close, and you don't have Landau quantization anymore at high energies. Okay. So that would be the treatment of the integer Hall effect. You'd look at the integer Hall effect geometry is really only coming from this effective mass tensor, and its only geometric property is really the shape of the Landau orbits, which define a kind of distance. So essentially the natural distance measure is to measure distances in diameters in a given direction of the Landau orbit. It gives you a natural count of why this is a metric. But the fractional Hall effect is not an effect that occurs because of Landau quantization directly. It doesn't occur unless you have interactions in the problem. And the interactions are the fundamental component of the fractional Hall effect. So to model this, apart from having a kinetic energy which will give you Landau quantization, you also have to have this interaction term. And this actually gives rise to 2 completely physically distinct sources of geometry in the problem. Essentially, a metric is really the definition of a circle. Okay? And so there's 2 kinds of circles in this problem. One is the circle defined by the Landau orbit around its guiding center. And the other source of geometry is the shape of the coulometric potentials around a point charge. Now, this one derives from the two-dimensional dynamics of two-dimensional band structure on the surface, while the interaction terms derive from the dielectric tensor in the 3-dimensional space on either side of this lattice plane. So unless there's a crystal symmetry axis normal to the lattice plane, and the magnetic flux is not got any component, is parallel to that crystal axis. In that situation, and there's a 3-fold or 4-fold or 6-fold crystal axis, then there'll be a point group symmetry, which will mean that these 2 shapes are the same. But in fact, a very common experiment in this field is to tilt the magnetic field, which destroys that symmetry. So on general grounds, there's no reason that this shape should be that shape. Okay? So when I use P here, the momentum, I mean the dynamical momentum. So it's got the vector potential built in. So the commutational relations of the momentum in a uniform magnetic field have something on the right, and this is the simple form. So again, I'm using a Euclidean plane and a Cartesian coordinate system, where this is the Euclidean metric, which will not play any role in anything. So in a uniform magnetic flux density, there's this well-known decomposition of the coordinate of the electron into the sum of displacement from the origin to the guiding center of the orbit plus the Landau radius vector of the orbit. So these 2 objects commute with each other. But individually, they have this non-commutative algebra. I think it's a Heisenberg algebra. But they have equal and opposite signs on the right-hand side. So when I add the 2 together to reconstruct the classical coordinate of the electron, that's the truly local one, then that, of course, commutes with itself as classical locality demands. But individually, these things basically obey quantum geometry. Okay. So if we now project into a single partially occupied Landau level, we have some filled levels, some empty levels, and we're going to focus on the interaction dynamics in this level here. We do the projection. Basically, we get a combination of the underlying Coulomb interaction and the form factors of the Landau level. So in general, we get a function, a different interaction potential in each Landau level. And of course, there's different physics in the lowest Landau level and the second Landau level, not because there's any fundamental difference between the lowest and second Landau level. It's just that the shape of this interaction gets weaker. And in fact, as you go up in the Landau levels, it's the quantum Hall effect is favored by the strong short-range repulsion, and charge ordering and density waves are favored by the long distance Coulomb tails of this thing. And as you go up in the Landau levels, it gets weaker in the middle and gets more dominated by the Coulomb stuff. So that's why the quantum Hall effect kind of goes away as I fill the Landau levels up, but it's purely an effect of the potential. So if I look at this Hamiltonian, which is now written in terms of these non-commuting variables, this, in some sense, is the entire contract we have for the fractional Hall effect. When you get a contract, it typically says something at the bottom that nothing that's not written in this contract can be taken account of, right? Well, this is enough to guarantee to give you a description of the fractional quantum Hall effect. It's got no relation of any kind to Galilean invariance, the structures of the Landau levels. It's just a fundamental non-commuting quantum problem. And if we look at its symmetries, at least for the uniform case, where I haven't put in the background, any background potentials, the fundamental symmetries of this actually also have no relation. They don't have any particular continuous rotational symmetry, but they do have a very striking symmetry. Apart from translational invariance, they have a 2D inversion symmetry just by the virtue of the two-body interaction between identical particles. And so this thing has a 180-degree rotation symmetry, which is the only thing that really the only part of rotational symmetries that goes over into this is needed for topological quantum field theories. You just need to know you can do a chiral 180-degree rotations is what you need to do braiding. So this is our basic problem. And so let's move on. And I'll come back to these later, but in terms of the quantum geometry, there's a basic algebra, which some people call a W algebra. This is actually written in an unrenormalized form. I'm not sure I'll get around to showing the renormalization of this algebra. Basically, this is the original form that Gervin, McDonald, and Platzman wrote it down in. It's called the sign algebra by some people. And this basically is the algebra, the generators of diffeomorphisms of the Landau, of the guiding centers. And a particular subgroup of this, which you can get by expanding this carefully, you basically have to, if you look at this carefully, there's a very singular U1 part, the Q equals 0 level, Q equals 0 part of this that has to be carefully subtracted out to make this algebra non-singular. And then you can expand it in the thermodynamic limit. And the lowest term to linear order in Q is going to, the term to zeroth order in Q is just will end up being charge fluctuations relative to the uniform background. The first order term will be the translation part, and the second order term is a crucial part, which is the generators of linear deformations of the Landau orbit. So actually, if you expand this to second order in Q, there's a kind of closed subgroup of this algebra, which is kind of like the Poincare group. It's formally like the Poincare group. So this is the algebra which causes distortions of the system. It squeezes. This squeezes the guiding centers in a uniform way. So it would take the x component could go to twice that x, 2x, and the y component could go to a half y in such a way it's an area preserving thing. And so the general structure of these deformations is controlled by parameterized by a symmetric, real symmetric second order tensor. And the thing is a pseudo rotation if its determinant is positive, it's a shear if it's 0, and or it's a squeeze if it's negative determinant. Okay. So now let's look at the Laughlin state. So Laughlin state is really a remarkable state because basically all the ideas, I think, in the fractional Hall effect have come from people looking at this, different people looking at the Laughlin state and seeing different things in it and finding different fruitful interpretations of it, right? And actually, Laughlin itself, it arrived out of the blue in some sense, because I know a bit about the history of how he found it. For reasons to do with looking what happened at the Coulomb interaction as the particles came together, he set about doing a numerical diagonalization of a three-particle system, right? And he found this thing. He found this, but the three-particle system was small enough he could end up, trying to work out what these wave functions were, and he saw something like the Laughlin wave function just at 3 particles. And actually, he submitted this, and he didn't circulate this as a preprint to any of the competitors. So this was actually held back. He submitted this in August of '82, and then a few months later, he had the whole theory worked out. So this is the Laughlin state, which has this thing which we all know and love. It looks like something straight out of complex analysis class. It's got Zi minus Zj to the m, and when you see the Slater determinant state of a filled Landau level with m equals 1, this looks extremely natural. Of course, it took someone to actually see this was the three-particle wave function to get the flash of inspiration. So I've written it with a half here. For various reasons you'll see, I've taken out, instead of a quarter L squared, I've renormalized it by a half. Okay, so the basic point is that essentially all the key ideas in this state have emerged from this, looking at this wave function. I'm going to describe a new feature which came from staring at this wave function, that it actually contains an emergent dynamical geometry, which was not at all clear from the way it was presented originally. So let's just let's just go through. First of all, we have the original formulation of Laughlin was in terms of lowest Landau level Galilean invariant Landau orbits. So we solved the Galilean invariant problem, which is harmonic oscillators, and we now I can write a Schrödinger type representation of the Landau level raising and lowering operators in terms of Z and Z star and their derivatives. Right? So from this one gets the famous result that the lowest Landau level wave functions, which are annihilated by the A, have to be holomorphic functions of Z times a Gaussian. Okay. And so if I fill the lowest Landau level, I get this uncorrelated state, a Slater determinant state, which is a van der Waals determinant. But if I fill it partially with this M here, I get something extremely different. I get a highly correlated state, the Laughlin state for M not equal to 1. And of course, it's fermions for odd m and bosons for even n. So let me now tell you the kind of received wisdom one has had for many years, which is actually not, in my view, not correct. Okay, it's a general kind of perceived wisdom. This is a holomorphic. The Laughlin wave function has a holomorphic character because it's a lowest Landau level wave function. Actually, that's not at all true, and in fact, it's not even a wave function. I'll come back to that. In its essential character. It's something else disguised as a lowest Landau level wave function. And it's also has a rotational invariance. This polynomial has a fixed total degree. And so again, the received wisdom of that, well, it's rotationally invariant because the Landau orbits are circular, et cetera, okay? And that's not true either. And the last thing that's not true is this thing has no continuous variable parameters. This was the remarkable feature about this state when it emerged in 1983. The only parameter that seemed to be variable was this integer topological parameter m, which determines the statistics and the filling factor. But hidden in the definition of Z is a metric. Z is a complex structure, and a complex structure is defined by a metric. So buried away, you ask the question, what is Z? The kind of obvious answer is, it's x plus iy, of course, right? But Z is not that. Z is something, a complex structure defined by a metric. So there's a hidden metric in this problem. Okay. So let's look at the guiding center variables. Again, these are the things that commute with the Landau raising and lowering operators, the Landau. And they also have a Schrödinger representation. It's almost the same as the Landau orbit raising operators, except I just swap Z for Z star in each of them, right? So these B operators, they have the property that they annihilate the Gaussian factor. just like the A's annihilate the Gaussian factor. And B, acting on a lowest Landau level state, multiplies the wave function by z. You pick up a half z from B dagger, half z from there, and you get the other half z from minus d by dz star. So actually, that says that what we should really be interpreting the Laughlin state as in a Heisenberg-type language, not a Schrödinger language. And that's no accident, because Schrödinger's language is not appropriate for quantum geometries, while Heisenberg is still valid for quantum geometries. So the Laughlin state written this way, the Gaussian factor has become the object that's annihilated by the B's. It's also annihilated by the A's, but they're not going to play any role in this thing. And the zi minus zj factor has become bi dagger minus bj dagger to the nth power. Okay. So this still has baggage floating around in it, because the way the Laughlin state was originally set up, I've actually used the same metric. I assumed the only metric in the problem was the Euclidean metric, which gave me the shape of the Landau orbits for Newtonian particles. And I made I used a kind of coherent, I used that same metric to define a coherent state for the B's. But there was no particular reason I should do that. So you can see I can do a Bogolubov transformation on these things, which is really just going to be one of these area-preserving linear squeezes that I talked about. And so this thing has a guiding center angular momentum, which is just b dagger b plus b dagger, which is actually the contraction of a metric with the generators of area-preserving, the SL2R generators. So hidden in this thing is a definition of the b dagger operators and the ground state via metric. And there was no particular reason. The only properties that is needed for this is that the metric is unimodular. It's got determinant 1. But there was no reason for it to be in any way related to the shape of the Landau orbit. So it's actually a free parameter of the theory. So we actually find then that this angular momentum has some other interesting properties. That, for example, if I work out this guiding center angular momentum, it actually differs. The total angular momentum, if you have Galilean invariance, has got the sign of it is one sign for the light cyclotron motion, the other sign for these. And there's a 0 point. They each have their own 0 point terms, which usually get cancelled. But the correct form includes the b dagger b plus bb dagger. And the angular momentum of the Laughlin droplet actually, as a function of the particle number, has two parts. It's got a part which goes like the square of the number of particles, which will turn out to be the number of composite bosons in the generalization, and another part that is proportional, linear in the number of composite bosons in the system. And this part, we had a discussion earlier, yesterday or something after the talks. This part is the statistical spin, which is related to the exchange factors. And this part is a completely separate topological quantity, which I call the geometrical spin. Okay. And again, these lambdas are these generators of area-preserving diffeomorphisms. So let's look at the changes from the original Laughlin formalism. We abandoned all this Galilean invariance stuff. In fact, we abandoned any detailed structures of the Landau level. That was just built into that ended up just causing some renormalizations of the effective interaction. We also abandoned use of the Euclidean background Euclidean metric as a metric and replaced it by a free parameter, which is a parameter of the Laughlin state, which in no way should be identified with either the Galilean metric or the Euclidean metric of the plane. Okay. Right. Okay, I think I already showed that, so let's pass that. So the Laughlin states with different values of this intrinsic metric are just related to each other by application of this linear area-preserving deformation, which all it does, it has an the action on the metric is an SL2R transformation of the metric of the system. So of course, if it's a finite droplet, the boundary shape gets changed too. But in the thermodynamic limit, this has all its action in the bulk. And the contrast between the fractional Hall effect and the integer Hall effect is in the field-Landau level. The bulk parts of the field-Landau level are completely unaffected by this change. The field-Landau level is a Slater determinant, and the Slater determinant is invariant under a change of basis within the Hilbert space that it spans, right? Okay, so what is the physical meaning of the Laughlin state? So of this metric. Okay, I'm going quite quickly actually. 15, yeah. So the Laughlin state is parameterized by this metric. What does it actually mean? And what it does, the Laughlin as opposed to the field-Landau level state is a correlated state where each electron is surrounded by a correlation hole. And in fact, that's the inspiration of the notion of flux attachment. The Laughlin state has a 1/3 filling, has 3 empty states attached to each particle. And flux, since there's 1 independent state per unit of flux through the system, the notion of flux attachment really means the notion of one single particle state attachment or orbital attachment. So Laughlin state has a rotational symmetry, and if I generate a rotational basis by using the metric around a point and put a particle at the center. This basis of single particle states defined by the metric is kind of like a series of onion rings that move out. And then the 1/3 state, the lowest 3 onion rings are given to the particle that sits at the center. If I do this squeezing of the thing, I'm actually changing the shape of this onion ring thing from one kind of ellipse to another kind of ellipse. And so what I'm doing is I'm changing the shape of the correlation hole, or the shape of the flux attachment around the particles. So the metric's function, the fundamental role of the metric is controlling the shape of the correlation hole. And since the field-Landau level doesn't have a correlation hole, it's an uncorrelated state, there is no metric properties of the field, none of this intrinsic metric in the field-Landau level. So it's a fundamental difference between the integer and the fractional Hall effect. Related, the fractional Hall effect is a genuine collective effect, while the integer Hall effect is just electrons sitting in some kind of background, okay. So you integrate out the electrons in the integer Hall effect, all you're left with the Chern-Simons term, which is a boundary condition between the electromagnetic fields above and below the surface. And that's all you've got. It's completely slave to whatever the external electromagnetic fields are, and because in the integer Hall effect all the currents flow at right angles to the electric field, there's no way to add or subtract any electromagnetic energy, at least if in the limit where you're not mixing Landau levels, right, in the integer Hall effect. Here there's a true internal dynamics that can store energy and propagate it. Okay. So then the question is, the Laughlin state's of course not the exact ground state of most of these real potentials. It's the exact ground state of a few very special model potentials. So the question then is, we can use the Laughlin state in its original inspirational form, which is a variational state, right? Before it was a variational state with no apparent free parameter. Now we realize it's got a free parameter. In the original application, there was an assumption of a rotational invariance of the system with a global rotational symmetry around the normal to the surface. So in some sense, you could do the variational problem of finding the metric that minimizes the energy without even any thought. It just comes out of group theory. It's got to be, the electrons repel each other. The whole wants to be equally distant in all directions, so obviously it's going to be the circular case. But now there's a real, if we have a model, an interaction which doesn't have a rotational symmetry, there's a real problem to find. You have to find which is the best Laughlin state, and of course as a variational problem. And so that actually suggests the Laughlin state as a kind of mean field state for this correlation hole. And in mean field theory, we usually have some magnetic system or something, and we find a set of directions of the spins or something that minimizes the energy, and the natural way to look for the excitations of this system is to now allow this mean field solution to now slowly vary in space and time away from the configuration that lowers the energy the best, right? So this is a system we should minimize the correlation energy. Okay, so again, looking at this, the generic Hamiltonian, the actual dependence of the projected system, it has this feature that it's a combination of the Fourier. You take the Fourier transform of the Baire interaction, you multiply it by the form factors, which is essentially the Fourier transform of the Landau orbit structure, multiply them together and Fourier transform back into space, and the fact that the form factor falls off as a Gaussian at large distances means that you can expand this Vn of R is analytic at short distances. So all the short distance singularities of the Coulomb interaction were completely regularized and smeared out. And one of the remarkable features of the quantum Hall case, from my viewpoint, is it's about the only condensed matter system that's ultraviolet complete. There's a continuum system, but it's regularized not by a lattice spacing like in the usual condensed matter system. It's regularized by this magnetic area, which is usually much larger than any microscopic atomic scale structure on the surface. So we have a continuum model with which is ultraviolet complete. Okay, so the Laughlin state actually has a special metric. Actually, it's got a family of special metrics. And if we look at it carefully, there are these potentials, interaction potentials, for which Laughlin is exact. And if I just take the simplest case, the 1/2 boson and the 1/3 fermion Laughlin states are both exact zero energy eigenstates of a model interaction which has depends on this quantity U, which is defined with respect to a metric. So U is R squared, defined by the metric which defines the state. Oops, what happened here? I didn't want to do that. My wrong button. And so we just A plus BU, which is like A plus BR squared e to the minus R squared, scaled to be precisely have a fall off which is controlled by the magnetic field density. So this is with A and B greater than 0, these are potentials for which both the 1/2 boson and the 1/3 fermion state are exact. So suppose we solve some potential, for example, this one. So let's take psi 0 to be the exact ground state of the system in that potential. If it's a special potential to which Laughlin exact, the ground state is a Laughlin state. If it's a different potential, it may be close to the Laughlin state or close to the Moore-Reed state or something else, but it's some state. And in fact, Gervin and McDonald and Platzman made what I think is the only kind of fundamental contribution to the issue of the gaps in the quantum Hall effect. Most work on the quantum Hall effect is either theoretically is shied away from the gaps. There have been some attempts at it, but mostly we take an axiomatic viewpoint. It's a topological quantum field theory. By definition, there's some gap. I don't want to know about that because I don't know how to calculate it. I'm going to work out the braiding statistics of the quasi-particles, and all the states have zero energy. So the TQFT structure has completely abolished all the notions of the energy, and I'm just interested in the braiding, which of course is perhaps the most interesting part. But if I'm actually interested in creating one of these states, I actually need to know something about why some interaction gives rise to a quantum Hall state and one doesn't, because I might be interested in trying to find out what I can do to get the level 3 Reed-Rizai state and Fibonacci anyons and stuff, right? So in some sense, knowing why there's a gap is a kind of piece of the problem which is kind of ignored in most of the topological based work. So anyway, going back, so if I now take the true ground state and I distort it by these things. Of course, the expectation value, the new state can be used, the distorted state can be used as a variational state for the energy. And of course, the variational energy of the distorted state is going to go up quadratically because it was by construction, it was the best one. So distortion always ruins it. So we actually find out these are second order tensors, so we end up with a fourth order tensor here, which is actually symmetric in the first two, symmetric in the second two, and symmetric under interchange of the two pairs. So it's really a 6 by 6 symmetric matrix. And this rank 4 tensor is a kind of shear modulus of the quantum Hall state, because these transformations are kind of error preserving. So, okay. And actually, the fundamental work of Gervin, McDonald, and Platzman, I've rewritten it in a slightly different way. They took the full sign algebra and acted with that on the quantum Hall, on the ground state, on the notional exact ground state, and they used the same kind of arguments as Feynman used for the roton in helium. You act with e to the ik dot r on the true ground state, and you can get an upper bound to the excitation spectrum, which is something they found it was something divided by the structure factor, or more precisely, the guiding center structure factor, which is the structure factor of these of the Gervin, McDonald, Platzman algebra operators. And they found this on the right-hand side was a rather messy expression, which they didn't interpret too well. They saw you could write it in terms of the structure factor of the integrals over the structure factor of the state, and they noticed that it went like k to the fourth at long wavelength. Okay, and what it turns out to be, the k to the fourth part, which is the top part of the Gervin, McDonald, Platzman relation, is actually precisely just this shear modulus tensor, the fourth order shear modulus tensor of the state when you stretch it. So the long wavelength part of the thing is just these shears. Okay. So let's look at what the actual excitation spectrum. Let's see. When did I start? I've got till 1:45, right? Yeah. So these are kind of numerical diagonalizations of these problems. These are actually diagonalizations of the problem for which the Laughlin state is exact. And this is the one for 1/3. And this is actually the state for which the Moore reads a three-body interaction, which is a repulsive three-body interaction, which makes the Moore-Reid state exact. And in both these cases, as Nick mentioned, there's no kind of mathematical progress on proving a lower bound to this thing. It's still a very interesting open problem. There's some similarities in some way to getting the Laughlin states have some kind of similarity to the AKLT states, for example, and Lieb and what's his name? They were able to get a lower bound by a rigorous lower bound to the gap in those cases by some series being convergent, and they could do it by some finite number of calculations. So it's still a really an interesting open problem, which goes back to things which Nick mentioned about what happens to the Laughlin state if you take the potential for which is exact and you let the value of m get bigger than 72, right? Which actually is clearly something to do with this gap comes down and goes negative about that. But so we would actually like to, there's still an interesting mathematical problem. How do I get a lower bound? How do I prove these model Hamiltonians have gaps, right? We can just prove they have, this is the maximum density at which they have a zero energy state, but there's actually no rigorous kind of lower bound type structure which tells you that. So numerics is the way that gives you the confidence to know that these model wave functions are gapped. And there you see this collective mode, which is a quasi-particle and quasi-hole come together, and they kind of fuse into the vacuum sector, but they don't, from the topological viewpoint, but they don't fuse into the vacuum. They end up fusing, and they end up somewhere up here, and they end up, this thing has an intrinsic angular momentum because of this special symmetry of the Laughlin states, and in fact that's related to their anything that has a conformal structure, the conformal group is an extension of a continuous rotation group. So anything that's conformal, of course, has that property. But there's the limiting case of this is a spin 2, or angular momentum 2 wave function, rather than the vacuum. And here in the more read case, you again see these things that there's actually, when you fuse the two non-abelian quasi-particles, they can either fuse in the fermionic or bosonic channel. The fermionic one is kind of lower, but they both head up into this jungle of, which in this case would be two of the neutral fermion modes that find a thing. And so what the bosonic one ends up at long wavelengths is precisely this Gervin-McDonald-Platzman number. So we actually know we have good wave functions for the Gervin-McDonald-Platzman thing, which is the boson case. So we kind of know what this ends up here, what it ends up at momentum 0. It would be interesting to find out what this is. There's some indications that there could be a kind of supersymmetry emerging that since both of the fermionic and bosonic ones end up at the same point, because the fermionic system ends up at spin 3 halves, which is sort of, if you want to interpret the bosonic one as something like some analog of the graviton, then the fermionic combination is crying out to be interpreted as some kind of analog of a gravitino. Okay. But anyway, so these are the structures of one sees these things. Okay. Right, and in fact, one sees some actually important aspects of the quantum Hall problem. I stressed that there was importance to inversion symmetry rather than rotation symmetry. 180-degree symmetry is kind of fundamental because a property of the quantum Hall states is, in the uniform case, they're always inversion symmetric. And it's probably true that any topological state, if it's not time reversal invariant, it's probably got to have an inversion symmetry, 180-degree inversion symmetry in these two systems. And you can see there's a kind of gap, a gap for any state that carries a momentum which breaks inversion symmetry. So there's all the states there's a gap for any state which is not inversion symmetric. In some sense, that's the more fundamental gap of these systems rather than a gap for charge excitations. It's a gap for dipole carrying excitations. Yeah. Okay, so
if you did not have a gap for dipole excitations, would the current be unquantized?
It would be a compressible system. In fact,
like the Wigner crystal.
Yeah, the Wigner crystal. In fact, interestingly, if you go back to this formula, instead of writing it, this formula is actually satisfied. The single mode approximation is a kind of harmonic approximation. Okay? And actually, this is true as an equality in any harmonic approximation. So if I actually take the Wigner crystal, or rather if I take the Wigner crystal and do the expansion and treat it that way, this is also true, except there's no gap in the system because, so this still k to the 4th. The energy gap goes like, I think it's k to the 3 halves, and the structure factor goes like k to the 5 halves in the thing. Right? So this actually is true, this kind of relation is a kind of harmonic relation or it satisfies an equality in a harmonic system, I'll put it that way, and an inequality in more generally. So I didn't catch that. You take the derivation of the thing is very much like you take this row of Q, which was sum over I e to the I Q dot R, where R is the guiding center, not the coordinate. You act on that on the true ground state. And this is a variational upper bound, an unnormalized variational upper bound for a system carrying a finite momentum Q not equal to 0. This thing is just a number. This thing just doesn't do anything when Q is equal to 0. It's just a number of particles in this case. It's actually 0 when you regularize it properly. So this kind of state doesn't exist at Q equals 0. It's a state that carries momentum. And in fact, if you go through the Gervin-McDonald-Platzman paper, they treat it as a rotationally invariant system. But the only part of their calculation that actually used anything connected with rotational invariance was actually k to minus k. So while they said they were treating it as they used a trick due to rotational invariance, they're using a trick due to inversion symmetry. So that they used the fact that the ground state was inversion symmetric, and that allows you to evaluate this quantity. And it turns out to be precisely this in the long wavelength limit. This the operator here ends up being the thing that at long wavelength does this. You have to expand this in powers of q. The first order term you pick up is q squared. Okay, which you can see because the structure factor of the expectation value of this goes like of two of these guys goes like q to the fourth. Rho q acting on the ground state has a normalization that goes like q squared and is actually just related to these operators acting on the thing.
So it makes no sense to break down this inversion symmetry further.
No, the inversion symmetry is actually, you get it even if the underlying system, once you've projected into the, I know where it was, here somewhere. Once you've projected into a Landau level and the particles are all the same, you can't avoid having inversion symmetry. You get it just because it's a two-body interaction between identical particles. Now, if you take a three-body interaction, that's not necessarily, it's going to have some parts. It doesn't have to have inversion symmetry because there's a complex thing. But the three-body ones that, for example, give you the Moore-Reed and these things, they all have inversion. They all have special kinds of three-body interactions which do have inversion symmetry. And all the model quantum Hall states, and presumably all the real ones of any in the clean translationally invariant background, their fundamental symmetries are inversion and. Although I didn't have it here, there's at least for the case of one-component systems, you can actually show that the inversion symmetry provides a powerful constraint on the common divisor of P and Q. For a system with only one kind of particle, by analyzing what happens on the torus and applying the principle that the ground state has to be inversion symmetric, you find that P and Q cannot have a common divisor greater than 2. You find there's a kind of quantum number structure there's a quantum number structure in a kind of Brillouin zone that you can define using the primitive value of Q. And there are 4 inversion symmetric points, pi 1 even 1 and 3 odd ones. And the usual quantum Hall states which have no common divisor in P and Q. So P is so 1/3 has 3 flux quanta attached to it, and the elementary charge is 1/3. Those guys, that always lies at Q equals 0. The Moore-Reed case is really 2/4, so it's elementary. It's actually 2 particles attached to 4 fluxes or 4 states, and the elementary charge is 1/4. And the Moore-Reed case, it occurs at that one, and that one. But you shouldn't be able to assign different quantum numbers to the members of a topological multiplet. You should be able to consider arbitrary linear combinations of the two. So it meant that you actually shouldn't be using the largest possible symmetry you can write down. You should be taking 2Q, which actually reduces this Brillouin zone to 1/4 of its size, and then puts in the new Brillouin zone, the quantum Hall states are all at Q equals 0, the translation invariant point. And in fact, that's what's been, that was what was done in this calculation here. This is actually to, again at 2/4, you find you have to use, there's a many-body quantum number scheme, and you have to use 1/4 of its zones. You get 4 quarter zones. And when the number of particles is even, the usual Pfaffian case, you pick up 3 copies of the bosonic sector and 1 copy of the fermionic sector. And when you do it for an odd number of particles, which still has a zero-energy state but can't be written as a Pfaffian, you get 3 copies of the fermionic case and 1 copy of the bosonic case. And that one's better because in that case, you can actually, the fermionic spectrum, you can get closer to k equals 0. There's a kind of, these are actually done by deforming the shape of the torus, but when you deform it too much, the spectrum gets crazy. So you want to keep, you can vary the allowed sets of quantum numbers you get by varying the shape of the torus, but you want to keep the shortest repeat distance to be larger than the size of. When the shortest repeat distance gets smaller than the size of the correlation hole, your state gets the properties. It doesn't affect the zero energy states, but it completely screws up the properties of the gap states. Okay, so let's move on. Yeah.
Is there a reason why the neutral fermion coincide the energy with the bosonic group at long wavelengths?
Yes, because long wavelength. This is a pair of. What is this? This is a non-abelian quasi-particle quasi-hole pair. They're the Ising-Ennion sector, right? So when they're far apart, they just have charge a quarter here and charge a quarter here, and you can't tell. And in one sector, there's somewhere associated with this pair, there's an unbound fermion, right? An unpaired fermion. But when they're pulled apart, that unpaired fermion is spread over a huge area, and it's not local anymore. That's the hiding of the quantum information stored in the thing. So they have to. You can't tell whether you're in the bosonic sector or the fermionic sector when they're far apart, because actually these fermions could be attached. They're independent. But as you bring them together, you see that so this is actually saying that when they come together, there's a kind of local kind of dipolar distortion, and the lower one is bound. A Majorana-type fermion has bound to it, while the other bosonic one doesn't. So this tells you there's some negative binding energy for the fermion degree of freedom as you bring the quasi-particle and hole together. But as they get very close together, the kind of curvature distortions around the system get spread out, and it becomes more like a wave. And on that basis, if the binding energy of the fermion, we'll come back to that. The fermion can only couple to the curvature itself. It can't couple to the spin connection, as we'll see. So it can't couple to a gauge field because and Majoranas don't couple to anything like that. It can only couple to the field itself, the curvature. And as you go to long wavelength, the curvature is spread out. So it makes kind of sense that you'd get a kind of supersymmetry out of this, because the binding energy of the Majorana fermion that distinguishes between the fermionic and bosonic sector will become smaller and smaller in that limit. Okay. So this is a kind of phonological picture of, I'm going to kind of motivate a picture of the quantum Hall's fluids by a picture of a quantum solid. So the basic unit in a quantum solid is the unit cell, right? And I've taken a very simple kind of 2D solid with one particle per unit cell. So the basic thing is, when is a solid stable? Basically, you can think of the stability of the solid as the binding between a vacancy, a particle, and the binding of a particle in its own vacancy, right? If I want to analyze whether helium-3, what pressure it melts and things, I would look at this following thing. I've got a particle if I pull this particle out, there's a repulsive interaction between the particles, so there'll be an attractive potential pulling me to the center of the vacancy. So then the question is the potential due to the vacancy strong enough to bind the particle itself, to form a solid in some sense as a condensation of a particle in a vacancy? So when the quantum zero-point motion of the particle is too big, it gets outside this thing, as it does in helium-3 or helium-4 at low pressures, then the thing melts, right? So this is this criterion for melting. So essentially, you should think of a solid. There's a kind of geometry of this system, which is the lattice shape or the unit cell shape, and the vacancy is approximately the shape of the unit cell. And then the question is the vacancy potential strong enough to bind the system? And that's the criterion for whether the solid is stable. So then, and the solid is gapped and things, if you forget about the phonons, right? For gapped for particle excitations. So if I have I can at least tell a similar fairy tale or story in the fractional Hall effect to do with flux attachment. Essentially what the flux attachment is doing, it's creating a kind of exclusion zone for this particle. It's saying these three orbitals belong to me, and it doesn't want anyone else to come into it, right? And the vortices sitting on that thing keep the other particles out. So if I just make a vacancy now by, say, 3 flux quanta of a certain, but choosing a certain shape, I will have a certain potential which here. And then the shape of the potential will vary according to the shape of the flux attachment I used. And then the question of whether the fractional Hall effect is stable and incompressible really boils down to whether the potential left by the flux attachment is strong enough to bind the particle or particles that want to sit into it. So in a sense, it's a continuum version of something like a Hubbard model. And in fact, the nu equals R Laughlin state, which is can be written exactly almost as a Hubbard model in some sense, except it's not on a lattice. It's on a set of orbitals, and it somehow has got this degree of freedom. It's got to choose the shape of the orbitals that want to avoid multiple occupancy. Okay. So the story I'm telling here is, anyway, the shape of the correlation hole is actually a quantum fluctuating object. Right? If we see that, there's some, but it's gapped because of the Chern-Simons terms. But interestingly, so a number of things. So the shape of the correlation hole is the metric, but if we have a non-uniform system where there's some reason for the electron density to be non-uniform, it actually can achieve that because you couple, it turns out, as we saw at the beginning, that there's the coupling that makes sense for the quantum Hall effect includes not just a coupling to the magnetic flux density, which is an external background field, but also a coupling to the Gaussian curvature of some metric. And if that metric is an intrinsic field, not an external background field, then the system can adjust itself by changing its metric to pile up some particles somewhere and other particles somewhere else. And it turns out that the coupling to that, of course, is a spin. And there's a second degree of freedom in this problem, which you can also think of, at least thinking about solids, at least ionic solids. So there's a second degree of freedom independent of changing the shape of the correlation hole, which is displacing the charge relative to the center of the flux. So changing the shape of the flux is a quadrupolar excitation, a tensor field, and there's a completely independent vector field, which is a dipolar field, which corresponds to distortions of the correlation hole that don't preserve its inversion symmetry about the center. Okay. So the spin, from this language, the spin here is part of the shift. As I said, there are actually two metrics in a simple quantum Hall state, one associated with the lambda orbits and one associated with the guiding centers. And in the shift picture, the shift is a combination of both of those two spins. But since they actually couple to physically distinct metrics, they shouldn't be combined in one thing. They should be thought of as two separate quantized objects. And the spin in the guiding center spin is easily calculated from this language. You look at the droplet, and the Laughlin state has this kind of pattern, has a characteristic pattern where you occupy the center of the droplet and the next two states are empty. So in fact, in regularizing this algebra, you have to do something to remove the uniform background. If you go back to where I wrote down the angular momentum of the droplet, there was a part that was super extensive that went like the square of the number of particles, and that's just the momentum you just get from a uniform charge distribution in magnetic field. So once you subtract that off, the uniform charge distribution, you just get left with the extensive part, which is the purely intrinsic geometric part here. Right? So what you have to do is to compare the occupation pattern 1, 0, 0 to the occupation pattern a third, the uniform background. And you see if I add these up, you really should count them, including the 0-point terms. That's a half, 3 halves, 5 halves. That one's L equals a half, that one's L equals 3 halves, so the difference of the two is -1. So the spin of the 1/3 Laughlin state is 1 or -1. And there's an argument about historical reasons about what sign convention you should use. That's the question of orientation. But this is the same sign as the cyclotron orbit spins. If I actually took the 2/3 Laughlin state, which would be a condensation of holes, where there was a hole at the center and the background 1,1 of occupied states, is actually minus s. So the Landau orbit spin is whatever it is. The guiding center spin is odd under particle hole transformations, and it vanishes identically in a integer quantum hole system. Okay. So the spin of the anti-Laughlin state, which would be a hole sitting in a background of 2 occupied orbitals, would actually have spin +1, okay? And the opposite sign from that of the cyclotron things. Okay, similarly, you actually, from this picture, it gives you some kind of, as a toy picture at least, it gives you some sort of, I think, some kind of insight into the Jane construction of the composite fermions with his idea of filling Landau level, fictitious Landau levels in kind of order of the Pauli principle. Here, the sequence 2/5, 3/7, you now have five levels in this state, and the 2/5 hierarchy Jane state is you fill the lowest 2 orbitals to get the right shift of the thing. Okay, so let's see, quarter of an hour left. Okay, so for the inhomogeneous system, I say we want to minimize the sum of the, not just the if we just minimize, if we have a translation invariant system, we'll have a kind of flat metric for the ground state in the thermodynamic limit. It'll be one value, but if I have to minimize the interaction, the correlation energy plus a one-body term, a local potential, then I can borrow some of the correlation energy to make this guy happier, which I do by piling some electrons up. So I can do a bit of Gaussian curvature locally to kind of pile it up. And so the electron density is actually tied to the spin times the Gaussian curvature. So the larger the spin, the smaller amount of distortion I need to get a large effect in the charge thing. So large spin means the thing is very floppy. And in fact, as you go down the Jane hierarchy sequence, the Laughlin state at 1/3 is 1 or -1. It's 1, 3, 6, 10, and diverging as I head towards the half-filled Landau level. And of course, the gap comes down like 1/S2 in this thing. So the larger the value of S, the floppier, the less. So the only strictly incompressible state is the filled Landau level. You can't beat the Pauli principle unless you're prepared to mix other Landau levels into the problem. For the other states, so that's like saying a spin chain with spin 1/2. Spin 0 is the one with the largest gap, right, of the integer spin chains. Well, that's a kind of stupid largest gap because only one state. So the most quantum of the quantum Hall states is a spin 1/2 case, which is nu equals 1/2 bosonic Laughlin state. Okay, so let's move on. So other things come out of this. If you go through, I'll come back to an effective theory in a minute or two. One can actually relate, as I say, the Q to the 4th the Q to the 4th behavior of the structure function that Gervin McDonald found along wavelength can actually be tied into the 0-point fluctuations of the shape of the intrinsic metric around its preferred shape. Right. So near the boundary again, from this viewpoint, it's not the electric field that matters, it's the gradient of the electric field that matters, which gives rise to a differential flow velocity near the edge, and it's the differential flow velocity which gives you the distortion effect. If all the electrons move at the same velocity, you just get kind of a boost. Nothing actually happens, right? But when they're flowing relative to each other, the distortions give rise to these dipolar distortions. So basically, this thing has a pattern of metrics which behaves like that at the boundary, has Gaussian curvature near it. Okay. So in the last few minutes, or last 10 minutes or whatever, so one issue which is kind of been thinking of for a long time in this problem is what is the effective theory of the system, not just the topological field theory, but the effective theory of the the fluid, which includes its gap and its long wavelength gapped excitations, right? And it would include things like the 0-point fluctuations of the field. So now we have a true effective theory with a kind of dynamical metric in it, right? So the question is, so back in 1990 or so, there were a number of, the idea at that time was to take non-relativistic particles and use Chern-Simons things to glue fluxes to them and come up with something. So natural thing is, after the interpretation of the Gervin's thing as a kind of, in terms of like something like a Bose fluid, right? A Ginsburg-Landau fluid is just a Ginsburg-Landau Chern-Simons theory. Well, initially that turned out, that looked kind of hopeful, and it had a kind of interesting spectrum, and people worked on it. And it got all the kind of topological parts right. So initially, people said this has to be right because it got all the topological parts right. But it turns out anything that contains the correct Chern-Simons thing will get the topological part right, even if the massive parts have got nothing to do with the reality, right? So I'm going to show what I think is an attempt to make a proper theory of this, although it's not just based on the thing that we actually are dealing with a Lagrangian, an effective Lagrangian for a dynamical 2D metric. And just as in a solid, you can look at a solid and you can see in some sense the acoustic phonons are the shape of the metric fluctuations in the solid. There's also the polarization things which couple to electric and magnetic field, which are really disturbances inside the unit cell that don't couple to its shape, the overall shape. That's a polarization field, and the quantum Hall fluids are a fluid, so they got an extra ingredient, which is a flow velocity. So we want something which couples at least three fields and together. And the basic picture then, you can think of a solid, you can actually think of we'll see we have actually, from this viewpoint, we get two conserved currents in this problem. One is the composite boson current, which is just the flow of the bosons. And the second thing is there's another current which can be derived from the metric, which is the Gaussian curvature current, which one way to do it, you can write the Gaussian curvature current as the curl of the spin connection if you want, or you can write it in other ways. But so we have two kind of things in the problem. The metric, the determinant of the metric, as in the usual case of a metric, will control the density of the composite bosons, and they will have some velocity relative to the so delta mu 0 is the background inertial frame of the crystal time axis. Okay, so that would be what one needs, and then what can one write down? And in fact, the basic structure has to have a topological parts and Hamiltonian parts, which now contain information about the energy that goes beyond the purely topological parts of the theory. And in this viewpoint, you get what you need in the thing. You'll get a Chern-Simons field, and what you can get if you want to write something that's independent of coordinate system, at least in the bulk, you have this, the analog of the gravitational Chern-Simons field will come in, which will contribute to the edge anomaly. So you have two anomalous terms. And what you get, which is very similar to the term one got in the Ginsburg-Landau theory, the thing that got everything right was basically coupling the gradient of a condensate field, which really just assures the Lagrange multiplier for conservation of the boson, of the composite boson current, to the Chern-Simons. Now it couples both to the Chern-Simons and with this spin parameter to the spin connection of the metric. And so again, but now you have, apart from these three terms, which are basically topological in character, you have the energetics of the problem. There'll be some correlation energy which favors a particular metric, but when you expand around it, you'll get this quadratic expansion in the fluctuations of the metric, which as a kind of shear tensor, there has to be a coupling to the polarization field, which is really just in the rest frame of the composite in the co-moving frame of the composite bosons, which are moving at velocity v. And there'll be a kinetic energy term, which in general will contain this background field related to the mass tensor. And in fact, out of this, you get the connections between dipole moment or polarization and the momentum. For example, this automatically gives you the correct relations for the momentum in a magnetic field, which is basically the polarization times the B. So if you actually semi-classically quantize this in a harmonic approximation around the ground state, you do in fact pick up the k to the fourth contributions to the 0-point fluctuations just from the harmonic modes. This term here, when you take it, this term here, the derivative of this, it's still a bit enigmatic what it's actually doing in the bulk, but the derivative of the geometric Chern-Simons term is an analog of the Cotton-York tensor, which only couples, which is traceless with respect to the metric, the local metric. So it actually only couples to the non-conformal fluctuations of the metric. It has no effect. In fact, there are no conformal fluctuations of the metric. The algebra the metric tensor satisfies is precisely the same algebra, the SL2, R algebra, and the determinant of the metric is the Casimir of the algebra, so it's got no quantum fluctuations. So, yeah. The spin quantum. This is the guiding. This is the guiding center spin quantum number, right? Is this one this is a geometrical spin associated with the. This is the spin connection of the dynamical metric. The statistical stuff is actually this is the K by 2 is the statistical spin. So in this picture, this is not looking at the action where you're looking at the topological order inside the thing. This is the action for the fluid without defects. Okay, it needs this is the statistical spin of the boson, which is PQ, is K. So the statistical spin is coming from that term. And the geometrical spin is a coupling to curvature. It seems to have no relation whatsoever to the statistics. This is the part coming from the Berry phases for dragging the vortices, which are dragged around as the particle moves. And this is to do with the coupling with this is to do with the fluctuations of with the metric coupling. So there seems to be no basic relation I can see between statistical and geometric spin. Okay, so I think I got to the end of my time, but if anyone has more questions, I guess I had some more stuff here.
Sorry, what's the conditions on the metric? It's like the only thing that it satisfies is like unimodularity, or are there any other constraints?
No, this metric is not. This metric has been scaled not to be unimodular. This metric has been scaled to, so the unimodular part of the shape fluctuations, right? The metric here has been. So I can separate out the metric into the determinant factor gives me the density of the composite bosons, right? I mean, it may make sense to factorize this as e to the I phi or as a scale factor times the unimodular metric. But in this form, this is the standard form for the density. So basically, it includes the size, yeah.
Actually, I had a question, Duncan. The metric seemed to be determined by properties like the band structure.
No, that's the extrinsic metric. The metric is actually the response of the fluid. The metric is the internal dynamical degree of the fluid. Because the Laughlin state, when you realize the Laughlin state is not just one state, it's a manifold of states parameterized by a metric. There's some point on that manifold but at least in a uniform system, there's one point in the manifold that minimizes it everywhere. But if I have some non-uniformity in the system, the shape can vary from point to point.
So this is describing fluctuations about the metric assumed in a Laughlin state around the one determined by the band structure.
The one determined by the minimizing the correlation energy. Yeah.
Well, I was assuming that by symmetries, the one determined by minimizing the correlation. Perhaps my assumption is wrong because of the fact that the Coulomb energy and the band structure favor different metrics.
Yeah. In general, they're not related. One comes from the dielectric tensor, and the other comes from the.
So, other questions?
If one considers parallel transport with respect to this metric, does it play any role in the physical picture?
Yeah, you pick up right, if you actually look at the expression for the Gaussian curvature in the Cartesian frame or whatever, it's got two parts. It's got a part which is quadratic which is a part which is linear in the second derivative of the metric, and then there's a secondary part which is quadratic in the first derivative of the metric. What you find is when you work out the thing, and of course you can try to get rid of that. You can make it at one point, but in general you've got these two parts to the thing. I think maybe it was even written down somewhere here. Yeah, this is actually the unimodular thing. There's also this is the Gaussian curvature of a unimodular metric. I guess there'd be the gradient of the determinant part is on top of that for me. You can see that there are two parts in it, in the shape part, which is the second derivative of the metric and quadratic in the first derivative. This part you actually can get out of if you do the full thing, from the variation of the thing, you first only find that, and the second term comes about from the Berry curvature. The second term which is needed to make the full formula comes from you go around the circle and you allow the metric to be changing as you go around the circle, and you calculate the Berry curvature for dragging the system around the path where its local metric changes, and you get this term, the two terms add together to give you the Gaussian curvature. It's the shape of the metric is the interactions determine what the shape of the correlation hole is. Okay, so the metric is really the shape of what stabilizes the incompressible state is the fact it forms this, it binds this flux to the particles, and the metric is really the shape of the flux attachment. So it's really the shape of the composite object. So it's really a metric because if you want to count, and of course which also impacts the surface, if you kind of measure distances, you're not measuring distances in meters with a yardstick kept in the lab. The intrinsic physical measure of distance is how many droplets you're away in a certain direction, right? And the metric, the intrinsic physical distance scale, so the theory should say that the scale that measures things in the basic units, like in a solid, the natural unit of length scales is how many unit cells you step that way, and that way. Here, the unit cell is replaced by an object, a composite object, which has a definite area and a definite shape, and you measure how many droplets away you have to go. So that's it's kind of like it's a continuum. It's something like a continuum a continuum version of a lattice, right? There's no lattice, so in a solid, the unit cells maintain their relationship. Two unit cells which are next door to each other will, even if there are acoustic phonons going through, will always remain next door to each other. The quantum Hall fluid has got these objects, but they don't maintain. There's differential flow can occur, so they don't maintain any kind. It's a liquid, so they don't maintain any one next to the other, but they do have this shape which allows you to measure kind of distances in the natural unit of the thing. Yeah.
Just one more question, maybe.
Yes. Galilean invariance has no place in condensed matter.
So if you calculate from your effective action the Hall conductivity,
Right.
I know that there's some work that assuming Galilean invariance, the Hall conductivity gets some corrections that are proportional to Hall viscosity. What do you get from this effective action?
You're talking about the long wavelength corrections.
Yes. Do you get a similar result?
Yeah, the whole viscosity is related to, in more general terms, the Berry phases for kind of applying these, going around the circuit of these area-preserving shears. So, in fact, even for the integer Hall effect, if you work it out for a non-Galilean invariant, you just take E of P. It's easier. I mean, it shouldn't be necessary, but it's easier to take an inversion symmetric E of. So you apply E of P equals E of minus P. That gives you a very neat. If the kinetic energy is even under momentum, which is consistent with the system having time reversal invariance when the magnetic field is removed, then those things it's quite straightforward to calculate those things, and you don't need to. You get formulas which relate to the shape. In fact, the expectation value of the generator of area-preserving diffeomorphisms is an expectation value of a symmetric tensor that actually replaces the effective mass tensor.
Thank you. Okay, I think we'll thank our speaker.